Thank you so much, John. I could listen to you all day. It feels like listening to Braveheart. Honestly, it's so inspiring. I wanted you to just listen to your inspiration. I do, like you, John, have an evangelical heart with regard to this technology. And as I bring up this first slide and show an image that the New York City commissioners or New York City Council asked us to prepare for them so that they could illustrate to the public and other lay people in politics how they were going to convert 900,000 buildings out of 1.1 million buildings in New York City over to geothermal exchange sourced heat pumps. So as you look at this, I just want you to realize this is something that 9 years ago, 10 years ago, we were working on because they've been thinking about it. They know that the only way to decarbonize buildings and electrify buildings involves geothermal energy networks. And we're going to talk about what the difference is between doing this and air source heat pumps, because a heat pump is a heat pump. It's just the difference in the source. And I would be remiss if I didn't share with you a little bit, very much as John was talking about, of my early days. 32 years ago, about this time, I was being interviewed on a morning show called Good Morning Tampa Bay, in the Tampa Bay, Florida is where it was. And we had just finished doing a geothermal system for an apartment complex. It was one of my first thermal energy network type systems. And they were so fascinated by this and the fact that there was no outside equipment and the energy consumption savings. And the host of the morning show, we were on site and they kept going from the studio back to us because we spent most of an hour talking about it in between other things. And toward the end, Rusty said to me, he said, Jay, he says, how long before everybody in the US has geothermal? And I thought about it for a minute, and it's really the first time I articulated this thought. I said, Rusty, I said, when it becomes a utility like city water, like sewer, like electricity, like cable and internet, which then was just cable, then everybody can do it. I said, we can't expect everybody to drill a borehole in their front yard to do this. That's ridiculous. That's as stupid as expecting everybody in a city to drill their own water well and install their own septic tank and leach field. And so that was the first time I had related that. And he said, well, how long do you think it will be before thermal energy networks become a reality at the municipal or infrastructure level for communities? And being younger and a little bit optimistic, I said, well, probably 5 years. Well, obviously it's 27 years later, but we're getting traction. So I'm not complaining. At least it's working. Heck, when I was in grade school in the early 70s, they were teaching us in the US, in Southern California, where I grew up, they were teaching us that by the time you get to high school, all cars will be electric and all power will be from solar energy. And they also told us that we in the US would be fully converted to the metric system. I gotta tell you, I am always amazed that the US is so difficult to change their ways. However, though it may be 50 years later, we are converting to electric transportation in cars. We have a lot of solar power, not nearly as fast as they said we would. The metric system, I don't know if we in the US, I can't even believe that fell apart. But my generation knew the metric system so well, it was hard to convert back to imperial, but the US did not adopt it. And therein lies the problem. We're creatures of habit. So that's probably the biggest thing. And thank goodness for the decarbonization movement and electrification movement. So I am going to go through some slides here and explain a little bit about what we have done in the industry and where we're going. First of all, I'd like to say that the elephant in the room, that this is probably the biggest problem. If you talk to the common person on the street, they think that we're doing great. They say, oh my goodness, I see all the windmills and I see all the solar panels and I see a lot of electric cars on the street. I think we're doing good. While the elephant in the room is the heating. It's 40% of our emissions. If we don't decarbonize our building heating, we're not going to get there. And so I love this political cartoon for this. It will take thermal energy networks to make heat pumps a reality for some of the reasons that I'm going to share. Some of the reasons are accessibility, but other reasons have to do with the electric demand, peak demand profile of our grid as we convert over to an all electric building stock. So a few of the advantages that people don't think about as we convert our buildings to thermal energy networks are that there's no more outdoor equipment to replace. We are much more hurricane and storm resilient. The longevity of the equipment goes up because that's the #1 reason for degradation, being outside in the weather. We, of course, eliminate combustion boilers. We also eliminate cooling towers, which I have a whole 4-hour presentation just on the benefits of that. So we have superior comfort in heating and cooling modes because of some thermodynamic properties of dealing with a more stable heat source and heat sink. The fact of the matter is that a heat pump is a heat pump. So as far as more cost, if we have a thermal energy network, it's the same price as any common garden variety heat pump to install a geothermal heat pump. It's just a water source piece of equipment. And of course, this infrastructure that ends up going in the ground is permanent infrastructure. Once it's in the ground, it's going to be there basically forever. Especially using the high density polyethylene materials and so forth that are going in, though the manufacturers typically warrant those for 50 years. The Plastic Pipe Institute thinks 100 years is more reasonable as an estimate of their lifespan. And in the back room, we know honestly that this type of material lasts more like 300 years, though we don't have the history to prove that. It's just an amazing product. So at any rate, these systems can go in with other infrastructure as we upgrade water lines, drinking water lines, sewer lines, even other infrastructure that may be going in. Maybe a little too late for the fiber optic networks, but we're using a lot of that information to help. A funny thing, and many of us will remember Ronald Reagan as a president of the United States in the 80s. Back in the 50s, he was a spokesman for the National Electric Manufacturers Association. And this is him actually pushing for live better electrically, buy a total electric gold medallion home. And isn't that amazing? Now, at the same time, what most people didn't know was going on was that the fossil fuel industry was installing natural gas pipelines faster and with more horsepower than anybody else. So during about the time that this was happening, the US had just come out of the Second World War and was going through a revolution of sorts of piping oil. As a matter of fact, we did our first big oil pipelines between Texas and New York because the German boats were sinking, the German subs were sinking our ships that were tankers that were taking oil from Texas up to New York. They sunk 76 of those ships before we even knew what happened. So they had an emergency funding of this transcontinental pipeline to get the oil from Texas to New York. And guess what? They piped it in 350 days, 2 separate pipelines in 350 days. They learned that the fossil fuel industry learned they could do this, and so they started piping natural gas. And over the next 20 years, 1.5 million miles of natural gas pipeline went in and connected to 40 million more homes than were already installed. So when the reason I tell that is twofold: to tell you how the natural gas distribution networks got such a foothold. There's now more than 2.5 million miles of natural gas pipeline in the ground, serving more like 80 million US customers. But the #1 cry for help or cry for foul is that we can't possibly put in these thermal energy networks. It's too much work. Not true. We did it in the 50s and 60s, and we continue to install natural gas, or at least we used to continue to install natural gas pipelines. But we can do anything we need to do, and we need to do this. We need to pipe thermal energy to every doorstep, starting with our big cities and even our suburbs, because they need it too, and moving on. Now, let's talk a little bit about why. The #1 complaint you'll hear from folks far and wide is that if we electrify all of our buildings, we will ruin our electric grid profile. It will cost trillions of dollars to install new electrical infrastructure to be able to handle the peak loads that we will see in the winter. So we already have a summer peak. Certainly in the US and throughout the world, there is, just as you see in this load profile at the American Society of Heating, Refrigeration, and Air Conditioning Engineers in Atlanta, Florida. I mean, Atlanta, look at me, Atlanta, Georgia. They installed ground source heat pumps on the 2nd floor and air source heat pumps on the 1st floor. And look in June and July and August, you can see this load profile of the air source heat pumps and the geothermal heat pumps. And you can say, okay, there's our peak load. And it's obvious the geothermal is better, but so what? It's like that proves that. But here's the real trick. Everybody's crying foul about, okay, we've got a summer peak load profile that we can manage. We'll never be able to handle a winter peak. Look what happened in Texas winter before last, when their electric grid almost collapsed due to a 1-week cold snap. So here lies the real illustration of what we can do. When you look at the air source heat pumps and you see this December, and Atlanta, Georgia is considered a southern climate. It's not even as bad as Washington, D.C., New York State, you name it, and go along the lines of latitude throughout the world, and you will see that both north of the equator and south of the equator. The further you get north, the colder it gets, or the further you get south. So even in Atlanta, we couldn't handle this. Their grid is designed and engineered to handle the summer peak load profile. If we have every building doing what these good air source heat pumps that were installed in 2010 are doing in the winter, what will we need? We'll need twice the electrical capacity. Yes, that will cost double-digit trillions of dollars. But what if we had an answer that gave us a load profile that didn't peak in the winter? Therein lies the secret to the success of thermal energy networks, because as you can see at this ASHRAE building, and as you can see in these two buildings in Oklahoma, US, this building was built identical to this building. One had air source heat pumps, one has geothermal heat pumps, and it was done in 2007. Look at that geothermal heat pump load profile. It is flat, as flat as you can get. And the utilities, National Grid, Con Ed, Eversource, you name it, right down the line, they're getting behind this because they see something. Yes, they know they're going to be turning off the spigot for natural gas. So this is their electric peak in the summertime, and the pink line is their natural gas peak in the wintertime. The geothermal heat pump solution shaves that summer peak, as you just saw in the other thing, and adds load to the winter peak. Just yesterday, our geothermal scientist, Nick Fry, who did his master's work overseas based on a US city, he did this illustration to show campus heating and cooling electricity profile changes to go to a geothermal solution. You can see the existing heating demand in kilowatts. There's data behind this, but let's just stay with the illustration. The existing cooling kilowatts and the geothermal heating kilowatts and the geothermal cooling kilowatts. Look at that shade there. And the thing is, you have all of these additional savings for the folks that are on the geothermal heat pump grid. The additional costs, yes, you can see compared to using natural gas, they're increasing their electric consumption in the winter. So there are additional electric costs in the winter. The overall net savings is extraordinary though. And we shave the peak and add shoulder electric consumption in the winter. The electric utilities love that. For those that may be watching, and I think that we have about 45 or 50 people on, some of you may not understand how heat pumps are rated. They're rated in coefficient of performance. And just to bring it all home, 1 kilowatt of electricity through an electric resistant space heater or anything like that is going to give you 3,412 BTUs of heat. 1 kilowatt of electricity into a geothermal heat pump is, and by the way, that 1 kilowatt isn't there to create heat. It's there to run a pump. What kind of a pump? A heat pump, like a water pump. If you buy a water pump, you pump water. If you buy a heat pump, you pump heat. Where do you pump heat from? The ground. So you use 1 kilowatt of energy to pump 4 kilowatts of heat from the ground or the thermal energy network pipeline to bring you a grand total of 5 kilowatts or 5 units of heat into the building. So that same kilowatt will produce 17,000 BTUs of heat. It's easy to see with a 5.0 coefficient of performance how we can take something that's extraordinarily peak heavy, like you saw with the air source heat pumps here and here, and we can shave that electrical consumption and level the grid. Another reason we want to do geothermal heat pump, sorry, clear my throat. Geothermal or ground coupled or thermal energy network heat pumps is this. And this is a real issue. It's a real infrastructure issue. These air source heat pumps, as you can see in this image where my cursor is right now, are subject to outside damage. These heat pumps were tossed about like so many child's toys after a hurricane in Florida swept across, and this was the same case with many, many rooftops. they get yanked right off of their foundations and blown around the building, around the rooftops. This is an image straight from New York City recently. And you can say, oh, this is so nice. This is so wonderful. Look at all the heat pumps going in. You know what? That gets old really fast because they leak on one another. They freeze in the wintertime. And they turn into rust buckets. And they may look a little handsome to begin with. But by and large, this is what we're going to end up with if we continue this air source heat pump revolution. It needs to be done infrastructure. I don't want to be the technician that is climbing this ladder to try to change a compressor in one of these. I don't think anybody here wants to be doing that. Or one of these, or one of these. It's not safe, it's just plain silly. Just a quick load profile of how air source heat pumps work at about 40, and I'm sorry, this is in US, at about 45 or 50 degrees Fahrenheit. They have a published operation that goes all the way down to -20. The fact is, as proven by the US Department of Energy in many, many different studies and other private entities, is once they hit about 20 degrees, when you consider all the defrost operations and everything else going on, they pretty much hit one COP. You might as well just be using an electric resistance heat strip. And therein lies the issue. And this is one of the DOE reports on several heat pumps throughout the United States. So I'm going to jump a little forward because I want to finish in about 10 minutes and provide some time for Q&A. So we're going to go into some practical information here. And let's do this one first. Let's talk about the difference between a natural gas distribution network and a thermal energy network. In a natural gas network, you need a pipe in the ground. So what is supplied through the pipe is natural gas, which goes to a furnace or boiler, a combustion appliance, to provide heating, typically heating only. A thermal energy network, what do you know? The same thing in the ground. It goes to a box that looks a lot like a furnace. It's an air moving or a water moving device, and it operates at 300% efficiency using the Carnot refrigeration cycle and provides not heating only, but heating and cooling and domestic hot water. What's the source? Thermal energy, earth exchange. If you go back and look at the illustration that we started with, you'll notice that it's a constant loop because it's renewable energy. Where is it picking up the energy? In the wintertime, where is it depositing the energy from the buildings in the summertime? Different in various heat sources and heat sinks, such as surface water exchange, such as wastewater thermal energy exchange, other infrastructure that might be available, such as subways, building structural pilings. Other imbalances can be handled by other exchange facilities that are developed for the thermal energy network. And everyone will need to be designed for their different thermal eccentricities, but it's all a solution that is a simple infrastructure solution. Pipe in the ground is all we need. A lovely example, there are hundreds of different hybrid variations of these things. And the reason I bring up this one from Cornell, they have a hybrid variation that is very unusual. They're on the surface of a lake that has 42 degree Fahrenheit water at the base of the lake year round. And they're able to operate their entire cooling loop, their chilled water loop for the campus, on just passive thermal energy exchange with the lake. We're not even beginning to look at all of the opportunities we have for thermal energy exchange. To not have to run chillers most of the year is extraordinary, and there are many examples of this. Where they are getting their heating energy now is from their combined heat and power plant. They create all of their own electricity by burning natural gas on site. What they are going to be doing, and they're drilling for presently, and this is not a low temperature application, but it just goes to show you can do anything you want in your city when you design and engineer it. And they got funding to go down to a deep direct, maybe an enhanced geothermal source they're drilling for now between 4 and 6 kilometers. And they will be decommissioning their combined heat and power plant and either creating their own electricity from enhanced geothermal, or at the very least, providing deep direct use energy for their heating loop. That's just one example, just to show that a more basic example is in 2016, the Cornell Bloomberg campus on Roosevelt Island, which is an island in right off the coast in New York City. They built, and you can see the building here in 2016, this campus, which used this thermal energy exchange loop field to come in through these headers and go to a central heat pump plant. You can see the exchanger here where some of the engineers are doing a tour with me back in perhaps 2018. So this is a standard geothermal exchange. It doesn't use a set like Cornell campus. It doesn't use a separate sink for the chilled water loop as compared to a source for the heating. Most of them just use heat pumps these days and do this exchange. I'll give a good example of why thermal energy exchange networks are the solution for which we are looking. We are on a project in Manhattan, New York City, that involves a complex that has 15 22-story apartment buildings that cover 5 city blocks here, and they need to figure out how to decarbonize all of these buildings. And you can see a 3D model that Nick Fry provided for us using the NREL program, UrbanOpt. And you can see that what NYSERDA, the New York State Energy Research and Development Authority, is asking us to do is, okay, you can do this. We understand you can do a thermal energy network for this, but we want you to cross property boundaries. We want to see what will happen if you diversify your load further than just one property owner. So what NYSERDA in New York State is doing is they're paying many different entities. There are actually 30 of these projects funded presently, and the next round will, I'm sure, triple that. But they are paying us to figure out how to cross boundaries. And here is why that's so important. In the middle of the winter, Penn South Cooperative Complex, which is home to 2,500 families, has a 4 megawatt thermal energy need that they produce using combustion heat from boilers in their central plant. Meanwhile, across the street, right here, is the US Postal Service sorting station for Manhattan. In that sorting station, what do you think they have? They have a huge data center. They have sorting equipment. They have thousands of people, thousands of machines sorting all of that outgoing and incoming mail. What does that convert to? What does that translate to? On the coldest day, it doesn't matter if it's minus 20 degrees or whatever, they have an 8 megawatt thermal rejection through cooling towers. All that we need to do is hydronically pipe that energy to the central energy plant and distribute it. And guess what? We have turned off the combustion for the entire complex. That energy is all being wasted through cooling towers right now. The same story is true. So all over the place in the middle of the winter, no matter where you are, there is a heating load where we are combusting energy in certain situations, combusting fuel, And all we have to do is get our buildings communicating. And what you see is several other opportunities here. We have been able to get a lot more neighbors involved in this, but this is one of the college campuses. Up here is the Amtrak station at Penn Station, where all of the subways meet together. And it goes on and on. So my point, as I finish this up, because I want to leave some time for Q&A, is that these thermal energy networks do what you see here. They reduce overall energy consumption. They eliminate the fossil fuels or reduce them dramatically. It increases electrical consumption in a very sane and safe way because of load diversification, just as you see here. High density mixed use in Massachusetts, for which this study was done for heat by Burrow-Happold, shows this close, meaning 52% of the energy annually is used for heating and 48% of the energy used annually is for cooling. It shows how a thermal energy network does solve really and truly all of the problems that we face with managing our thermal energy using thermal energy networks. And I'm going to leave it right there and invite any questions and comments. I'll be quiet while we let our host take over again.